331. Let's go. There is a thin horizontal disk of disk of radius r equal to 10 centimeters is located within a cylindrical cavity filled with oil whose viscosity is given. Oh, so now you're using viscosity as well. Okay, it's a horizontal disk, radius something, is located within a cylindrical cavity filled with oil whose viscosity is this thing. The clearance between the disk and the horizontal planes of the cavity is equal to 1 millimeter. Okay, so like this thing. Yeah, okay, so this should be h, right? So from here all the way till here. Okay, find the power developed by the viscous forces acting on the disk when it rotates with the angular velocity omega equal to 60 radians per second. The end effects are to be neglected. Well, that's new. The end effects are to be neglected, huh? uh okay. Very interesting. So what can we do? Although we don't have the viscous forces in our equation, so the original equation that we are always using, should we just use the usual formula for viscosity, or should we actually put our viscous forces in here and then try to do something with it? I don't know. Well, I mean, this thing is of course just so our volumetric force density, right? Because of viscosity, that's given by mu times del square of u vector, right? So that's a vector, of course. Uh, yeah, and okay, think about it. Does the vertical thing even matter? Actually, maybe it does. Maybe it does after all. What assumptions can you make in this question? I mean, since it's viscosity, right? This is a viscous fluid. What we can do is we can assume that this whole layer, right? So the boundaries of this container, those have u equal to 0. Okay, and the u values close to this disk, that's the same thing as the vector of the disk, right, at that particular point. So of the surface that's moving. Yeah, that looks cool. And then what? So what kind of distribution should we be dealing with? Should it just be like a simple linear gradient from here to here? Maybe it's going to work out, because who knows. uh Yeah, this is actually very weird. We really need the del squared in the polar coordinates, sorry, the cylindrical coordinates, right? Otherwise, how am I going to do that? Yeah, but then moreover, they didn't actually tell us how the viscous forces actually act. So I think it's okay to go for the most simple view, which will just be that, yeah, there's a linear gradient, and yeah, there's a linear gradient. That is, it's not, sorry, there's a constant gradient. So the gradient is not changing for our u vectors. We can assume that, can't you? Right, so we'll just see if that works or not. Right? So we don't know whether or not that. Okay, so I think you could always add the pressure such that this would work, right? So just assume a fluid flow and then figure out the pressure from that. Yeah, that would work. And moreover, over here, the pressure actually doesn't even matter, because the pressure is not going to create any kind of torque, right? I mean, in the vertical direction, that is. And in fact, yeah, like it just won't create any torque, because so torque over here that will cancel with the torque because of the pressure from here, right? It's because of the radial symmetry. I think that would work, right? So our assumptions are right, that your fluid speed is the velocity, in fact. So this is of this form omega r, and then it's linearly increasing. Okay, right. So it should be. So I'm just taking this upper layer of fluid and not talking about the lower fluid, but still. So the y coordinate, right? That so we'll just say this thing is the y equal to 0 plane, and then we are going up. Okay. So then you will just have u vector equal to, so for a linear distribution, that is for a constant gradient along the y direction. you could just have u vector is equal to omega r. That's over here. Okay, then you just want so over here it should be 0, right? Okay, so this complete height, which is just h upon h, and then if you're going upward, okay, so how much of it is remaining? That's something. You know what? Now let's actually go the opposite way. We'll just say this thing, so the bottommost layer, that is the y equal to 0 plane, and then we'll go up till we reach this this plate, and that will be our y equal to h, right? And then we'll just think about the flow velocity for this lower part of the fluid. Then you just have u vector equal to omega r upon h times y. Okay, and of course this in the tangential direction, so along t hat. And now really we just have to see whether or not this satisfies our continuity equation, because the pressure equation, using that you will find pressure gradient, and then yeah, so we don't care about the pressure, do we? I don't think so. Yeah, this should work out. So just, yeah, the pressure will be whatever it will be. We don't care about that. If this works, then it works. So that other equation, the pressure equation, it's satisfied automatically because we don't know what the pressures are. So you can just assume that the pressures are such that it works out. And the continuity equation, well, that you can do. Okay, so for the continuity equation, um, all you just want is that the divergence of u should be 0, and then we know how the divergence will be in the cylindrical coordinates. It's just this thing, partial ur upon r plus, oops, partial ur upon partial r plus ur upon r plus partial ut upon r partial theta plus partial uz upon partial z. Now uz is 0, doesn't matter, right? Similarly, ur is 0, so these two terms don't matter. And then ut is just the same thing as the speed itself. So it's just this thing. And right, so just do this thing. So like omega r upon h times y, this thing is not dependent on the theta at all. So you can just say omega r y upon h. And then you got 1 upon r over there. And this times dt hat upon d theta, which just is r hat, I think. Wait, no, it's negative r hat. Fine. And then this is oh, this doesn't look so good, unfortunately. Yeah, this doesn't look good. Well, this is not 0. It should have been 0 though. Why is this not 0? So what we're saying is that this kind of distribution, or in fact any kind of distribution with just a t hat component, it won't work. Unless, of course, this thing also depends on t hat. Huh. Wait, am I? Oh, okay. I get what went wrong. I get what. When I said ut, it's not the ut vector. It's just ut, the magnitude of the ut vector, which is just this part. We don't have to worry about this part in that case. So then the partial upon partial theta of this part, it's 0, of course, because it's independent of theta. Which means that, yeah, this actually will work. This is a good, right? So this will work. And I know I said that I don't want to use that viscous term in our Eulerian equation that we had earlier. I don't want to introduce that. But then maybe I should. Maybe I should, you know. Because, okay, so what kind of forces do we really want to consider? We want to consider only the forces that are parallel, sorry, perpendicular to our r vector. Yes. So any radial forces, we don't consider those. Okay. And yes, there is a radial gradient of u vector, so there might be the second partial derivative with respect to r or whatever that might be there. We don't consider that because, right. So then just consider what, yeah, just consider the gradient along the y-axis, right? Yeah. So then partial u upon partial x, sorry, partial y, that will just be omega r upon h, right? Yes, that's a constant everywhere. So the, yeah, the viscous force put on this thing from the lower surface, Well, that will just be this thing. So from like a certain area dA on this disk, the force will be what? dA omega r upon h times. Okay, that is not there. It is this thing. That's our gradient times the viscosity area gradient. Yeah, that's the thing. So that will be the force. Now we don't want the force, we want the torque. So this times of r, right? Because this is in the tangential direction, so it should be this times of r. That's going to give us the thing. Okay, so our d tau, which is our small torque because of the area, this thing. Okay, that will be this thing. But that's only from one of the surfaces. You actually want from both surfaces, right? So we'll just have 2 times of this thing, right? So what did we get? We just got that d tau is equal to this thing's like 2 eta omega square omega r square upon h. And then what is dA really? dA can be written as r dr d theta or r d theta, whatever you prefer. So this will just be what? 2 eta omega r power 3 dr upon h and then d theta. So that's our d tau. So when you integrate over the surface, or I should say over this disk, does that actually make sense? I don't know. So only over one of the surfaces of the disk, right? What you will get is tau is equal to, so this d here, right, the angular integration, so integration with respect to theta, just that will come out. Just 2 pi comes out, and then take out all the constants as well. So just have what, 4 pi theta on h omega, yeah, all of that comes out. And just this thing, integration of r power 3 dr from r equal to 0 to capital R, I think. Yeah, so it will just be this thing is r power 4 upon 4, and yeah, just pi eta omega r power 4 upon h. That's the torque that this will put on it. All right. So what you want? You want the wait. Eta is 0.08 p. Wait, what? But what does p mean? It's not. Is this the pressure or something? No, that doesn't make any sense. It won't make sense because units will be different. Eta is definitely not in units of pressure, is it? Eta times length times per second. Sorry, eta times area and then times per second is equal to Newton meters. Yeah, no, it won't be pressure. It can't be. So this is probably the unit of viscosity. What was it called? I don't remember it. But yeah, it's the unit. Let me just say maybe it's the SI unit. I don't know about it, but whatever. So this is the thing, right? This is our torque. And what do you want, by the way? You want the power developed by the viscous forces acting on the disk when it rotates with the angular velocity. This thing. Right. So the power developed, which is like the d upon d of half I omega squared. Isn't that the thing? That's the power developed because changing current energy. This will just be what? This will be I omega and then alpha. I alpha is just the tau thing and that is of omega. So it's tau omega. Right. That will just be what? Pi eta omega squared r power 4 upon h. That's the power or the instantaneous power. Actually, it should be negative of that because, yeah, this is actually going to slow that down, right? So it should be negative of this thing, but whatever. So it's negative this thing. Yeah, that's the power. And what will this be? I don't want to calculate this, but then they did give us everything that we need. So I think we have to. Just to be negative pi is, just keep it as pi for now. Then you want eta. Eta is 0.08. I'm assuming this thing is a SI unit, but whatever. That times omega squared, so 60 squared, 3600. So this cancels. Then that times r power 4. R is 10 centimeters, is like 10 power negative 1 meters, right? So 10 power negative 4 meter power 4 upon h. What is h? 1 millimeters, 10 power negative 3. Okay, just 10 power negative 1. So this will be what? Negative pi times 8 times 36 times 0.1, right? I guess. So 36 times 8 is what? 24, and 40, which is 288, right? So 28.8 times pi, which is 3.14. I think that's gonna work out. Yeah. Yeah, it should work out, I think. So 314,288. Okay, for 2, 3 carried on, 8, and 3, 6. What am I doing? 32 and then 8, which is 11. So 1 carried on. Then 8, 3, 24, 24, and then just 25. Then 0, same stuff, 2, 5, 1, 2, 0, 0, 2, 6, 2, 8. And carried on, it's just 3, 2 is 5. 0, 1 carried on. Fine. So something like this, right? And then 3 of these guys, so 90.4 something. 90 is a good approximation. So yeah, so it will just be 90. I mean, you can always do the, what do they call it? The error analysis. So over here you have 3 significant figures. There's also 3 significant figures. So in the end, what you should have is, oh wait, well, okay, that's 0.1. Everything over there. Okay, this is kind of complicated, isn't it? Yeah, we don't know for a fact this is 28.8 or not actually. This got very complicated. Okay, but then they did give us the perfect values for eta, omega squared, and r. So yeah, like this stuff is actually a pure number. So you only have to care about this thing. That's what is yeah, not a pure number. It's an approximation. So 3 significant figures is what we look for. So 90.4, good enough, right? Okay. In fact, I'll round it up to 90.5. Yeah, whatever, 90.4 is also good. Who cares? Next question, 332. Okay. A long cylinder of radius r is displaced along its axis with a constant velocity inside a stationary coaxial cylinder of radius r2. Displaced along its axis? What do you mean? Constant velocity. Oh, okay. I think I get what's going on. So this is the bigger cylinder. You have a smaller cylinder over here, and this is being pulled basically, right? The space between the cylinders is filled with viscous liquid. Find the viscosity of the liquid as a function of radius r. What do you mean by viscosity of the, huh? From the axis of the cylinder. The flow is laminar. Uh, I don't understand what's going on. And it's a long cylinder, right? So just to extend this thing. This is displaced, right? Where did that go? It's displaced along its axis with a constant velocity v naught. So it's actually being pulled by a constant velocity. Okay. The space between the cylinders is filled with viscous liquid. Okay, cool. Inside a stationary coaxial cylinder of radius r2. This is very weird. The shape, okay, sorry, the space between the cylinders filled with viscous liquid. Find the velocity of the liquid as a, oh, sorry. The velocity of, for a second, I thought it was viscosity. It's the velocity of the liquid as a function of distance r from the axis of cylinders. The flow is laminar, that's what you're saying. And it's a viscous liquid, right? Okay. Wait, the flow is laminar. Something doesn't make sense. Wait, if there's velocity over there, okay, so this is supposed to be infinitely big, right? So you have this very big and long, sorry, just very long cylinder, and then inside you have another very long cylinder, and then this thing is being pulled with velocity v naught. you want to figure out the velocity profile of uh, the liquid over here, right? Yeah, basically. So once again, can we do the same thing as we did last time? Can we assume that, you know, that the gradient with respect to r is constant? So then we just have this thing, right? Okay, first of all, set up some coordinates. So this is the axis from which we'll figure out our distance r. Yeah, and then this thing, so we'll rotate like this. This is theta, whatever. We don't need to show that in this figure because we won't be using it in the end. What's our z coordinate? This is our z coordinate, right? Yeah, so this will be our z coordinate, or maybe this should be our z coordinate. Who knows? So thing is that I'm proposing is u vector is equal to um, what should I say? It will be equal to v naught. Okay. Yeah. Wait a second. So this is r. This will be like r1. This will be r2, right? So v naught upon distance from here. That will just be what? I think that is the way it should be, right? So distance from here just r2 minus r1, and that times of the distance that you now will have, which is just r2 minus r, right? Is this going to work out? I don't know, but hopefully it will. So like u vector is basically this thing, v naught r2 upon r2 minus r1, which is kind of a constant, minus this thing. So v naught r. Oh, and it should be vector. It's actually along the z hat direction. So z hat direction, right? Yeah. So that's the way it should be. And yeah, looks good. Got negative v naught, whatever. Just put it like that. Now, once again, let's check our divergence. So it's supposed to be UR upon, well, there is no UR, neither is there any UT. So those two terms not there. It's just the UZ that we look for, which is like partial UZ upon partial Z. But then once again, this is not a function of Z in the first place. So this, yeah, it actually satisfies the divergence equal to zero condition. The pressure stuff, well, yeah, that only gives us the pressure. It doesn't actually give us any useful information, right? So we'll actually just not think about that. So yeah, this looks like a good thing, right? Okay, and now what? Uh, of course, we'll just figure out the velocity gradient at this point. And right, wait, what do you actually have to figure out though? Where did that go? Find the velocity of the liquid as a function of distance r from the axis of the liquid. Well, I mean, I already did this, right? If flow is laminar, yes, okay, that works out. Sure, it does look laminar. Huh, so I already got the velocity. Well, that was unexpected. It works, right? It satisfies the divergence equal to zero condition. It also, what could be the thing? I mean, what about the viscosity stuff? Okay, that's the next question. What other conditions do you need? The flow is laminar. Now I'm not able to understand what exactly I should be doing. I mean, isn't this the same thing as Poiseuille's equation, but with this new surface inside, right? Yeah, it's the same thing as that, right? Uh, and in that case, you did have the velocity profile as something like this. Or, wait, no. I don't think, okay, this is wrong. This might be wrong, actually. I don't know for sure it's wrong or not. Um, so the way they actually, so the way we used to derive the velocity profile for the Poisson's equation was that you would take this everything inside of it as the system, right, and assume that the system is actually moving uniform without any acceleration, which would mean that the viscous force on this would be zero. Wait, what? The viscous force on this would be, no, okay, no, that's not the thing. Right. The viscous force is still there. The thing is that, oh yeah, okay, there's like difference of pressure, isn't it? Oh, it's getting complicated, isn't it? Uh, what about the pressure though? Is the pressure over here the same thing as pressure over there, or what? So for this particular fluid flow, or in fact any fluid flow that is completely in the radial direction, the divergence is still zero, right? So it doesn't matter if the fluid is like this or the profile is like this or whatever, right? So we don't actually need to limit ourselves to functions like these, right? So then what other thing can we use? This is getting complicated. Okay, think about it. Will the Bernoulli's equation, okay, that doesn't work, of course, because we have to integrate along a streamline. Here you can't do that. Oof. At least use that equation that you have. Okay, no, you will also need the viscosity for that and whatnot. This is getting complicated, isn't it? Without a full equation, how can I even show you anything about the pressure over here? Do we just have to assume that the pressure is the same throughout this cross section? That doesn't look very convincing. But that's how we derive the fluid resistance equation, right? Okay, so I will have to use the full equation in that case. So, okay, let's just scroll back. What was the thing? The equation was rho dV upon dt, where, okay, actually the u vector, right? So du vector upon dt, that is equal to what? This f vector thing minus delta p, sorry, f minus del operator applied on p. It's like del vector of pressure, right? So the gradient of pressure. Yeah, that will have the thing. But when you have viscous forces acting as well, your f vector, this actually contains an extra term. So there's the, of course, rho g that you have to have, and there's another term that you need, which is the viscous term. So I think it was like this thing, del squared, so mu times del squared, where I'll just say eta. This is the equation of viscosity, then del squared, and then you have u vector, right? This was the thing probably. And of course, del square is just this thing, partial square upon partial x square plus partial square upon partial y square plus partial square upon partial z square. And then that's applied on our u vector, right? Yeah, that is the thing. Yeah, I think that was the equation. Or was it something different? Or f vector contained this, right? Oh god, it's getting complicated now. Okay, let's just focus on one term. Let's just focus on this thing. So partial squared uy upon partial xy. What does this actually mean? So you have this, uh, so you have these blocks of fluid, right? And this thing, let's just say it's moving with u1. Or let's say, okay, this is moving with uy in this direction. Sorry, ux in this direction. Wait, what? Okay, I think we should be talking about this thing instead. So partial squared ux upon partial y squared. Yes, this is moving with ux in this direction. This is moving with ux minus, so partial with respect to y of ux in this direction, and it's moving with partial with respect to, oops, okay, ux plus partial with respect to x, sorry, with respect to y of ux in that direction, right? I guess, yeah. I don't think it's good to do it like this. This is not helping, is it? Okay, let's just do it in some other way. So this is, okay, moving with ux direction, sorry, ux velocity in that x direction, and this is our y coordinate. The force between this and that, that will just be what? That will be eta times this area, which is just what, dy times d. No, wait, not dy times dz. It's something different, I think. This is our y direction, right? It should be dx times dz. Okay, so eta dx dz, and then you have the velocity gradient, so just partial ux upon partial y. This is in the x hat or I hat direction or whatever. So that's the force, right? Uh, put on it by this. Actually, it should be negative of this thing. So like as it goes, this has higher speed, this has lower speed. That's what I'm assuming, right? Yeah. Oh, it should be this times of, wait, no, the gradient times area times viscosity. That is in fact the force. Yes, right. And that's the force put on this thing, right? By this. And similarly, force put on this by this, that will be, so let's just say it's one, that is representing, that's the force put by one on this middle block, and then the force put on the middle block by two, that will be what, eta dx dy partial ux upon partial y 2, right? Yeah, so this will just be what, eta dx dy, and then partial upon partial y of partial ux upon partial y, that times dy, because this thing is dy, right? And yeah, this is what this thing minus that thing is, right? So in the end, you just get eta dv partial squared ux upon partial y squared. So of course, as your gradient increases, this is like having a force like that, right? Okay, that makes perfect sense. So our f vector should not have that negative. Yeah, it should not be negative. It should be actually positive. That's right. Yeah, that's how it should be. I think that's correct. Okay, so that's why you have the positive sign over there, not negative. And if you want to see why this term is the way it is, like why is the viscous force just this thing, eta del squared u vector, but I don't have a good explanation for this thing. The reason is that the partial squared ux upon partial x squared term, that can't be explained the way other terms can be, right? So other terms can be explained by just, considering what happens as you move along y and as you move along all other directions, right? Yeah, and then you just have shearing and all that stuff. But then for the partial ux squared upon partial x squared term, you actually need to think of it in terms of, diffusion of momentum. So particles are going from 2 to 1, right? That's what's happening, and something like that, right? So that's why you will have something like this as the term. Okay. So now we have the complete equation. So the complete equation is just rho du vector upon dt equal to rho g vector plus eta del squared u vector minus del vector e. All right. Okay, now what I have to show is that for a velocity distribution where the velocity is just in the z hat direction and doesn't have any components in the t hat and r hat directions, the pressure across this cross section, it's the same everywhere on this cross section. That's what I have to prove, right? So let's try to do it. First of all, du vector upon dt, as this thing moves, it's only in the z hat direction. So its component on the xy plane, nothing, right? So we don't have to worry about that. And of course, there's a changing pressure in z hat direction, but then in the other two directions, we don't have to worry. So we just think about what's happening in the xy plane, right? So this term doesn't matter because there is no xy component of u vector. So yeah. Then rho g vector, let's assume that this is not that big and then it actually doesn't really matter. So you can get rid of that term as well. I know this probably is not correct to do, but then I will I will just do it. I'll assume that this is like this cross section is not very big and then this effect can be neglected. So yeah, then you will, because I want more symmetric distribution, right? So if there's this g vector in the in the y hat direction everywhere, it just, yeah, it doesn't look good. So I will not think about it. Then you will have this thing, del vector p is equal to eta del square of u. Now once again, u vector doesn't have any xy components, right? So when you just have partial squared, right? Okay, so wait, yeah, okay, because it doesn't have any xy component, this automatically, like this whole thing will in fact automatically not have any xy components. Now, what does that actually mean? You know what? Actually, I should say that u vector is equal to u times z hat, right? So that, yeah, so it will just be what? And then u is actually a function of, so it's a function of r and z. It's not a function of theta, right? Okay, what am I doing? Because del squared we don't have in in a polar, sorry, in the cylindrical coordinates right now, so this is not going to work. But yeah, this is still a good justification because this is having only a z hat in there, so you can think of it like eta del squared u and then all of that z hat, right? That makes sense. So this is just a scalar and it's along the z hat direction, but then what that means is that there is no xy component. So the gradient of p in the xy plane is 0, right? There's a gradient along the z hat direction, but not along the xy direction. What that means is that throughout this cross section, it's the same pressure everywhere. So it doesn't matter what kind of distribution you have for velocity, it's still the same pressure everywhere. It is weird. Yeah, it really is. I didn't think this would be the way to work out. But okay, interesting. Are we sure that there is really just no distribution of pressure? But then, yeah, it seems that is the thing, in fact. Yeah. Okay, whatever. So yeah, throughout this, the pressure is the same. That's what we get it. Okay, then you can have any kind of distribution and then pressure is the same. So because of that, the Poisson's equations derivation that we usually do, it's actually correct, right? So that is the way to go. So the way the derivation goes is like just consider this cylindrical volume with another cylindrical volume taken out of it, whatever, right? And you just do the F equal to ma thing on this. So you will have a change in the pressure along the z direction, of course. So you just say delta p that times the area of this thing, which is just pi r squared minus, let's just say this thing is r naught, so minus r pi times r squared minus r naught squared. This is the force put on it by the pressure, right? That's equal to the viscous force, which is just like u vector in that direction, whatever. It will just be eta. The area of this whole thing is, let's just say this thing is L. So we just have L. Oh god. Right, and then you want 2 pi r. That's this area. Okay. You just have this gradient. So this will just be du upon dr, right? Yeah. So delta p upon L. Okay, let's not go into that right now. We'll just, right. So delta p times, okay, first of all, cancel that stuff out. Delta p upon L, right? This thing times r square minus r naught square. If I just put that inside, okay, not right now. We'll do that in meantime. So this will be eta L du upon dr. So that dr actually goes over here, just becomes this thing. Awesome. And now you can integrate to get u, right? Yes. So we just have eta. Oh, that L is not here anymore. Oh, that 2 is here though. So you just have this. And also there's this r. So you have to put that. Yeah. So what you have is delta p upon L times r squared minus r naught squared upon r. And I would say that delta p upon L is actually the same for any kind of this volume, right? So this thing is just the same thing as partial p upon partial z, which will say is a constant, right? I know you might be thinking, why should it actually should be negative of this thing? Because the pressure should be higher over here and less over here. So that's why negative of it. So you might be thinking that why should we assume it's a constant? Because the equations that we had told us. Yeah, right, because we assumed that u vector was the same. It's not a function of z, right? Yeah, and okay, so it's not a function of z. What am I right? Okay, what should I say? The partial p upon partial z is equal to a constant. How do I even describe this? like the z direction. There's ah, but shouldn't this be a constant? Why would this be something different? Okay, let's not run into that right now. We'll just say it's delta p upon L for now. I know it's a constant because that's what Poisson's equations tell. Poisson's equation tells us that you know delta p upon L is in fact a constant, as you can see over here. But fine, for now it's not going to that. Delta p upon L. Okay, you got this thing. Dr is equal to 2 eta. Then you just have du. Now just integrate this thing. So you just have 2 eta u going from, let's say, from here to here. So from capital R to small r, right? So this will be R naught and this will be capital R, right? So this will just be 0 minus, or in fact, let's go the opposite way. So, okay, from here to here, right? That's what I want to do. Then it should be this thing. It should be u minus 0, right? So 2 eta u, that's equal to what? That's the integration of this thing, right? Yeah. Okay. It's delta p upon L. Then it's the integration from R is equal to capital R till R is equal to, what should I say? Wait, is this actually correct or what? Yeah, I mean, okay, du upon E is in fact a positive quantity. So as, no, it's not a positive quantity. It's a negative quantity, right? Oh, then you should have a negative over there. Right, okay, so it should actually be negative involved. Then just go from, you know, small r to capital R, right? Yeah, that looks cool. So it's just the integration of this thing, which is r minus r naught square upon r, and then you got er. Why is this including a natural log term? I don't like this. Yeah, I definitely don't like this. If r naught was 0 somehow, then this would mean work out perfectly, but it's not 0, so you will have a natural log term. I don't like this. Just have 2 eta u is equal to, oh god, are you serious about this? Why is this having, oh, this doesn't look good. Yeah, but that is what I got, so we have to deal with it. This is just delta p upon L, and then r squared upon 2, so it's like r squared minus r squared upon 2 minus r naught squared natural log of r, natural log of capital R upon small r. Okay, cool. So what you have, u is equal to delta p upon 2 eta L times this stuff. So just r squared upon 2 minus r squared upon 2 plus r naught squared natural log of small r upon capital R. Should be 2 over the not r. Okay, that's our final conclusion, that so u vector will be given by delta p. This is kind of weird. Okay, delta p upon L though. Wait, so why don't we just put small r equal to 0 in there? Oh, sorry, small r equal to r naught over there, and because that's gonna give us the final. Yeah, so that will just be the v thing. So we just have v naught is equal to delta p upon 2 eta L times all of that stuff, just a constant, right? Just some constant. What that means is, like, yeah, delta p upon L is actually a constant, which means you can write that thing as negative partial p upon partial z. So stop writing this. We don't do that. So just write u vector is equal to negative 1 upon 2 eta partial p upon partial z, okay, times of this stuff. So I have to say partial x, so we'll just say the x coordinate is along the axis, right? Yeah, we'll have this stuff. So r squared, just very weird. Maybe this is not the best way. Oh, I think we know what we can do. We can, of course, we already figured out what v is, right? So just put r is equal to r naught, but then you will get v, right? So just divide those two equations. You just get like u upon v naught. That will be what? I don't like this exactly, but then whatever. You know what? No, the best equation would really be this thing, because this is the most useful one at least. So what did we get? We just got u vector is equal to uh, negative 1 upon 2 eta partial b. Actually, you know what? Partial b upon partial z looks like it's not constant everywhere. It is in fact constant, right? So we have to show that. So instead of that, just do this thing delta p upon 2 eta l. Okay, and we just have this thing. So r1 is r squared upon 2, which in this case is just r2 squared minus r squared upon 2, and then you have plus r1 squared natural log of r upon r2. Yeah, that looks cool. Okay, next question. Although we are introducing new symbols over here, which is the pressure and the length, or the change in pressure and length, but still I think this is the better answer. Next, 333. Okay, a fluid viscosity is something fills the space between two long coaxial cylinders of radius. Didn't we just do that? Yeah, I mean, we just did that, right? Oh, okay, no, these two are similar questions, but different. Okay, fluid with viscosity eta fills the space between two long coaxial cylinders of radius r1 r2. The inner cylinder, the inner cylinder is stationary while the outer one is rotated with a constant angular velocity omega 2. The fluid flow is laminar, taking into account that the friction force acting on the unit area of a cylindrical surface of radius r is defined by the formula this thing. Okay, wait, what? Taking into account that the friction force acting on a unit area of a cylindrical surface of radius r is defined by the formula sigma is equal to eta r. What's this thing? Partial omega upon partial rt. Okay, what is sigma though? That's the friction force per unit area, right? So, okay, interesting. What do you want to find? You want to find the angular velocity of the rotating field as a function of radius r, okay, and the moment of the friction forces acting on the unit length of the outer cylinder. On a unit length of the outer cylinder, what? What does the unit length even mean in this context? Oh, okay, so the length of the cylinder, right? So, the moment upon that length, right? That explains it, right? And the cylinders are same. Okay, whatever, doesn't really matter whether or not they are the same length. Just assume the inner one is actually really long. Okay, fine, whatever. So let's try to think about it. First of all, this formula is this formula correct or what? So eta r partial omega upon partial r, you are saying, right? So I think this formula is like, what was the thing? Eta, then you want the area of the element, okay. Then you want partial u upon partial r, right? But then remember that u is just omega r, so then you want partial 1 partial r of omega r, which is beta dA, and this is kind of weird. Are we sure this actually is going to work or not? Uh, doesn't look promising to me. Oh, it should be partial u upon partial r, yes. Understood. Okay. What else do we have to take into account? Fluid is flowing like that, right? Okay. It's the tangential direction and everything. Sure. Uh, yeah, well, that is the thing, in fact. Along t hat not changing, along z hat not changing, along r hat it is changing, and that's why you have this thing, right? And it's in the t hat direction. Sure. This should have worked. I mean, this should have been the formula, right? Partial upon partial r of omega r. It should be like partial omega upon partial r times r plus uh, plus just omega, right? That would have been the thing, but it's not. So why is this term not there? I guess it should have been there. And then r is out of it. Okay, fine. I get it. It's just you're just taking this term. But then what about this term? Is this not supposed to be there? Oh God. Come on, think about it. Must be something that's doable. I guess this might work. So like partial u vector upon partial r. Probably. It could work. Who knows? I mean, on a single element, you have that thing that the force is just related to partial squared upon partial x squared of u, right? So yeah. Okay. So for a layer, what would the thing be? Or not actually a layer, everything below it, right? Yes. I mean, that is what we took, right? This is the thing. So then this was the thing, right? Partial u vector upon partial r. But then once again, u vector is along t hat, and t hat does not change when changing r. So what's exactly going on? This should not have been the formula. Spherical surface of radius r is in this formula. No, I don't get it. How is this formula correct? What I got is very different than this thing. What I got is eta dA partial omega partial r times r plus omega. This is not this thing. Ah, taking into account the friction force. Friction force? You mean the viscous force, right? What friction force? What are you talking about? I don't know. I just don't know why this term is not here. This is shorter than what, but that would mean that the last question that I did would be wrong, right? Okay, no, that was the different. It was different. This thing, no, that doesn't involve a cylindrical surface. It involves this circular surface, a disc, whatever. So this would not be wrong. Okay, what about this thing? Okay, that's not even. There is no friction in this case. It's just completely static, so that is okay. So, but still, why is there this omega omitted? This should have been there, right? Or am I missing something? Am I missing something? Is this formula correct or what? Shouldn't there be this omega involved as well? Yeah, it's starting to not make sense. Partial omega, partial. Why would that not be there? Just want the velocity gradient, sure. It's gonna work out. You want the force on that. Yeah, that's right. Something's not making sense. That's like a torque, right? Okay, that's in the tangential direction. I get that. Anything else that could be related to tangential directions and the pressure? No. It can't be involved. It's only the viscous forces, of course. So if the flow is completely tangential. Why is the viscous force not having this omega term associated with it? Okay, think about it. Shouldn't there be this omega term? No, I have no idea. Okay, so we just use the formula they gave us, although I don't think it's correct, or at least I don't know why it's correct. And then we'll try to figure out what. Okay, so according to them, the force is given by this thing. So the net force on this kind of surface, right? What would that be, right? You just have the force. It's like maybe that's not the best thing to be doing, but whatever. I don't know. So F is equal to 2 pi R L times eta R, so like R squared over there. Then you got partial omega or partial R, right? That is the force. Yeah. Wait, okay. We don't actually want the force. We just want the torque, right? We don't want the force actually because the force vector would be zero, right? So we don't actually want that. We just want the torque, which is given by integration of r vector cross. So that our force would just be this thing sigma vector times the area vector times the area. In fact, sorry, why am I writing it sigma vector? It should be sigma times the area vector or something like that, or sigma area. That also works. And we don't need this cross really. It just r sigma a integration of this thing. So then sigma is a constant throughout the surface. So just sigma integration of, I should say dA, okay, RdA, right? Yeah, that will be a torque, which is, so like RdA. Yeah, well, think about it. But each of these, right? And R is the same, right? R is the same throughout the surface. We can just take that out as well. So just sigma R, and then integration of dA is just the area. So it's just sigma R times 2 pi Rn. That's the torque. So our torque is just sigma times 2 pi r squared L. So then it's just this thing, right? So it's 2 pi eta L is r squared as r cubed, in fact. Okay, that was r squared. Now it's r cubed because there's that r over there as well. And then you want partial omega partial r. Yes. This is over there, then this is over. That's done. This is also done. And then you have L, and r is involved, 2 pi. Yeah, works out. That's our torque. Now, because of steady state condition, what we can say is that um, this torque is zero. Wait, no, that can't be. That just can't be. Huh. Okay, this is a torque for that inner thing. Okay. What about, okay, so you got, so it's the top view of the whole thing. So this is our axis. This is our axis through which we are actually rotating everything. Okay. I just say, maybe it's not the axis. We just have this cylinder which is rotating. Okay. Then there's fluid across it. Okay. And then you have this thing, in fact, right? So this layer of fluid, which is not thin, which is supposed to be thick, I just drew it like that. This actually has the same angular momentum, which means, I mean, same angular momentum throughout, which means that the torque is actually constant because the change in the torque as you go from here, so from this surface to that surface, it's zero. If it was not zero, the angular momentum would be changing. So you are saying that this torque is the torque put by us on this thing, right? Yeah, basically. Yeah, because that's what we have to do in order to keep this rotating with the same angular velocity. So that torque will just be the inertia of this inner cylinder times its omega. Wait, no, no, no. That will be angular momentum, sorry. Uh, the torque at that point, wait, something's not right about this thing. Anyway, all we care about is like this is a constant, right? So this is a constant. What does that mean? That means that, right? I just write this is like d omega upon dr. So dr upon r power 3 times tau is equal to 2 pi eta L. Then you got d omega. So 2 pi eta L omega is equal to, so actually the change in omega, right? So from where to where are you actually going? This was which question? 333, right? Yes, the inside cylinder is stationary. So we'll just go from R1 to some R, then it's just omega over there because we're going from 0 to omega. Okay, this is equal to, this is like R power negative 3, which integrate that, it's supposed to be negative 1 actually, right? Negative 1, so negative tau upon 2, and then this integrates it. Of course, that is a key thing, just 1 upon R squared, right? That's what we have been doing. Sure, so 1 upon R squared going from R equal to R1 to some other R. Should be like 1 upon R squared minus 1 upon R1 squared. Right, so this will just be tau upon 2 and then 1 upon R1 squared minus 1 upon R squared. That makes sense. Okay, so now we have angular velocity as a function of R. So what do you want, by the way? So angular velocity as a function of the radius that we got. Okay. Oh, and the inside is actually rotating with omega 2, right? So when you put R equal to R1 over here, sorry, R equal to what? R2 over there, right? So when you put R equal to R2, you just get omega 2, right? Yeah. So then the equation that we have is like omega upon, because first of all, we don't know what tau is. So that becomes a problematic thing. But anyway, omega upon omega 2 is equal to 1 upon R1 squared minus 1 upon R squared upon 1 upon R1 squared minus 1 upon R2 squared. So then that cancels everything. Yeah. This will be what? R squared minus R1 squared upon R squared, and then you have R1 squared. Oh, it should be R1 squared over there as well. So R1 squared, R2 squared upon R1 squared minus R2 squared minus what am I writing? Yeah, this is the thing, right? So some stuff cancels. It's this thing. So you can say omega is equal to omega 2 times all of this, right? It is R2 squared upon R1 squared times, oh sorry, R2 squared upon R squared times uh, R squared minus R1 squared upon R2 squared minus R1 squared. Yeah, that looks cool. So that's the answer to our first part, although that's not the answer I was hoping to get. This is the answer I was hoping to get, right? Okay. So tau is once again the torque that we are putting on the inner cylinder. Sorry. Well, yeah, we have to put on some torque to let it not rotate, right? Yeah, so the magnitude of that torque is what we are considering as tau. This is the equation that we are going to be using the most because it's the most useful one. And then our answer is this thing. Then let's go to B. B is the moment of the friction forces acting on the unit length of the outer cylinder. Moment of the friction force acting on the unit length of the outer cylinder. Oh yeah, I mean that is the tau thing that we just got, right? Just use that. Now that is per unit length, right? So tau upon L is what we look for. That just equal to what? So it's just 4 pi omega what? Omega 2, right? Yeah. Actually, it will be any omega. Yeah, right. Why even do that? You could put any kind of omega, right? Yeah, anything at any R will actually work, but then there's only one thing that we know, so that's why I'm gonna put that. So it's omega 2 upon all of this, just 1 upon R1 squared, it's 1 upon R2 squared. This can be written like this thing, R1 squared, R2 squared, upon R2 squared minus R1 squared. Okay, that's this thing. Next question. 334. A tube of length L and radius R carries a steady flow of fluid whose density is rho and viscosity eta. The fluid flow viscosity depends on the radius R from the axis of tube. As this thing, okay. V is equal to V naught times 1 minus R squared upon R squared. Find the volume of the fluid flowing across the section of the tube per minute time. That is easy to do. Yeah. And the kinetic energy of the fluid within the tube's volume, that's also easy to do, no big deal. The friction force exerted on the tube by the fluid. Okay, that's something that you will have to do. Okay, fine. I mean, it's not that hard because, yeah, it can be done, no big deal. The pressure difference at the ends of the tube. Yeah, doable. Um, the kind of thing that we got right. So u vector was given by it should be just u, not u vector, because we are just giving the magnitude. So if somehow your R1 was 0, this would just become what? This would just become delta P upon 2 eta L times R2 so as R1, sorry, R2 so as R squared upon 2, right? Yeah, just that. Sure. And so writing that using V naught or something. So when R is equal to 0, your U becomes the maximum. That is the V naught thing or whatever. So yes, this thing is in fact identical to the usual Poisson equation thing, right? So it's the same thing as this thing. It's just a special case of that, in fact. But of course, V naught is the maximum speed, which is at the center, right? Yeah. Okay. So what do you want? First, the volume of. So we can just use the fluid resistance from that, right? Yeah. Oh, okay. We can't do that directly, unfortunately. But once again, just write down the equation. It was what? Delta P upon Q is equal to 8 eta L upon R power 4, right? Let me just actually scroll up to see if that is the equation or not. Uh, Come on. Yeah, so it's 8 eta L upon R power 4. Yes, that's the thing. Right? It looks correct. What is this? We don't want this. 334. Okay, but we won't be using this actually. We'll just do it using integration. So you gave us the velocity. We want to figure out the volume of the fluid flowing through the section of the tube, right? Yeah. It is integration of, so that cross-section area just 2 pi r dr. And that times of the velocity, which is just v naught times 1 minus r squared upon r squared. Yeah. This will be the dq thing, and then integration of this thing from r equal to 0 to capital R. That's our q, which is what? So just have 2 pi v naught, then you have integration through to capital R of that comes out, that comes inside just r minus r cube upon r squared, and then you got dr over there. So this will just be what? 2 pi v naught, then you will have r squared upon 2 minus r power 4 upon 4r squared. So this r squared upon 4, which is combined just r squared upon 4, which will be pi v naught r squared upon 2, right? Yeah. So that's the answer for first question. Okay, just pi v naught r squared upon 2. Okay, awesome. Second question. Second is what? The kinetic energy of the fluid within the tube's volume. So it's the same thing as this thing, except so just the volume of this thing that you'll have to be looking for, which is so 2 pi r dr times L, right? Yeah, that's the volume. So that times the density, that will give us the mass. So now this is the mass, and you want half m, and then v squared. V is just the square of that thing, right? Yeah, this is the thing, right? So that's our kinetic energy. Looks cool. It's just what? This cancels just a pi L rho, and you got RDR side. Just go to RDR. This definition that comes out, yeah, so just V naught squared outside. Okay, and then you will just have this thing. So 1 minus 2r squared upon capital R squared, and then plus r power 4 upon r power 4. You want to integrate this thing, but okay, first of all, r inside, so it will be this thing r minus r cubed, and then you got r power 5 actually. Okay, just call that outside. So the thing that we'll get is pi L rho V naught squared, and then r squared will come out. And inside we'll just have, first of all, 1 upon 2, then minus 2 upon 3, plus, I think 1 upon 5. Yeah. So this will be what? So this is a, what this thing is just 1 minus 1 upon 3. So just 1 upon 2 minus 1 minus 1 upon 3, which is like, what am I even doing? Just do it properly. 3 minus 4 is 1, 1 upon 6, right? So 1 upon 6 plus, sorry, negative 1 upon 6, plus 1 upon 5, which is 1 upon 30. So let's just do this thing. Yeah, that's our continuous. Okay, next what we look for is the friction force exerted by the tube, on the tube by the fluid. Okay, cool. So you got V, what's dV upon dr, right? Okay, wait a second, right, yeah, dV upon dr, that is the pressure gradient, sorry, that's the velocity gradient, right? Yes, that is equal to negative 2 uh negative 2 V naught, and then you will just have r upon r. We don't care about what this actually is, we just care about magnitude. So yeah, that's our gradient, 2 V naught r upon r squared. So our force will just be what? 2 pi r l, capital R L, right? That's our area, viscosity, the velocity gradient, which is just this thing. So 2 V naught r equal to capital R, right? So just 2 V naught upon r. Yeah. Some stuff cancels, just 4 pi eta L V naught, right? And what do you want? Yeah, just that much. Okay, P. The pressure difference at the ends of the tube, right? For that, we can just use this formula. So we already have Q as a function of V naught, so just put that in there. What do you have? Just delta P is equal to 8 eta L upon R power 4 times Q, which is pi V naught R squared upon 2. Or you could always use this force kinetic part. So this is the viscous force, and this is equal to pi r squared. So yeah, like 4 pi eta L V naught is equal to pi r squared times delta P, right? Yeah, which means delta P is just equal to, so if what we did was correct, just 4 eta L V naught upon r power 2. Let's see if that is the thing actually. And there's a pi, so that got cancelled out. Wait, that should have got cancelled. Why is that not? Why is that here? Uh, yeah, something doesn't feel correct. It should not have been here. Why is it in that case? Spy we not ask. I mean, whoa, that is not supposed to be happening. Why is there a factor of pi in there when it's not supposed to be there? It's going to just pi r squared delta p, right? Yeah, right. So k is this thing. Oh god, something's not making sense. Uh, what could have gone wrong? Why is this not working? The viscous force is equal to the delta P times R. Yeah, okay, that must have been the thing. But then maybe there was a factor of pi and we just didn't see that. Okay. Oh yeah, it's like pi R power 4 over this. Sorry. This should actually be this thing. Uh, pi R power 4. Right, that explains it. Okay. Yeah, right. So this is a 334. 334, not 24. Right, pressure difference at the ends of the tube. You can do it like this thing. So it will just be what? Yeah, this thing. And let's also do it in that way. So it will have in our Q thing. Okay, you should have this thing. Okay, fine. So this cancels. It's R squared over here. This is 4 eta L V naught upon, yeah, okay, 4 eta L V naught upon just R power 2. Yes, that's the thing, which is exactly what we got. Yes. Okay, next question. So I have to remember this thing. The fluid resistance is 8 eta L upon pi R power 4. 335. In the arrangement shown in figure 1.90, a viscous, a viscous liquid whose density is this thing flows along a tube out of the white tank A. Okay, fine. Find the velocity of the liquid flow if h1 is equal to 10 centimeter, h2 equal to 20 centimeter, and h3 is equal to 35 centimeter. Okay, all the distances L are equal. Wait, it's flowing out of what? A viscous fluid whose density is something. It flows along the tube of a wide, so it's a viscous fluid, right? That's the main thing, right? So the resistance is the same everywhere, which means that um, okay, what was the thing? So like the Q value is the same, right? So delta P is equal to the resistance that you will have, which is actually proportional to L. So some constant times L, and that some constant depends on the fluid and the geometry of the cross section. So K times L, and that times Q, right? So this is constant. So delta P is proportional to L, right? So from here to here, you will have, let's say, one delta P. From here to here, you will just have two delta P, right? Yeah, which is, as you can see, it's just linearly decreasing. That makes sense. Okay. So what do you have to figure out? Find the velocity of the liquid flow. If h1 is equal to this thing, okay, whatever. All the distances L are equal. They didn't actually give us what this area is, huh? Yeah. Density is rho equal to the flows along a tube out of a white tank A. Find the velocity of the liquid flow. Wait, how do I do that? Wait, they give us what the rho is. They also gave us what it's kind of weird thing. If h1 is equal to 10 centimeter and then something else maybe. Wait, okay, what was that formula? So delta P is equal to 4 eta L V naught upon R squared, right? Yes. Okay, interesting. So just after this starts, it starts to flow in this tube. At the very start, the velocity profile is in fact the same everywhere, and then it starts to actually become more and more like what we have over here, so parabolic, right? So in this region, you can at least apply the Bernoulli's equation, right? Yeah. Uh, Maybe there is some kind of stream along which you can in fact apply Bernoulli's equation. Who knows? Might be the case. No, that's not right. You can't do it anywhere. Yeah, okay, you can't do it anywhere. So you can't apply Bernoulli's equation. How am I going to get this in that case? We don't know what's happening at the very start, unfortunately. How do you get the velocity? Oh, this doesn't make any sense. How do I get the velocity in that case? And um, velocity of liquid flow in which, like, okay, velocity of liquid flow, but then there are multiple velocities, right? So in the center, it's the highest velocity, and then near the boundaries, it's zero. So what velocity are you talking about, and where are you talking about? No, I don't get it. Which velocity, first of all, and how do I get it? They gave us the density, cool. It's a viscous liquid, whatever. They gave us the density, and then they gave us a white tank, okay, whatever. Find the velocity of liquid flow. If H1 is given, H2 is given, H3 is given. They gave us the heights at different points, okay. All the distances L are equal. Ah, not making sense. So the hydrostatic pressure over there, that's the thing about the cross section is that it has the same pressure throughout, but then the velocity is different, right? Yeah, the velocity is different everywhere. So how do I do it? So since the velocity is different everywhere, the pressure at the middle is what this thing is measuring, right? I mean, okay, it doesn't even matter because the pressure is the same everywhere. So it is measuring just the pressure at the boundary as well. Okay, so that's the pressure it's measuring. Okay, cool. Uh, what else? What else do we know? So they actually did give us what the pressures are because they gave us H2, H1, and H3, right? They also gave us these lengths. Hey, so we can actually figure out what Q should be, right? Because I think, yeah, so you know what delta P is, you know what L is, and okay, you can't know what K is, unfortunately. And what you want? You want the velocity of the liquid flow. Hmm, this is weird. So you can of course do this thing, right? So delta P equal to 4 eta L E naught upon all that stuff. So it has 1 upon R squared over there. So this part 4 eta L upon, so 4 eta upon R squared. This is dependent on the geometry and the fluid itself. So we don't have to worry about that. Okay, they also give the density, whatever. So instead of writing this equation, we can write it like this. So it will be delta P is equal to K, some constant, times the length times V naught, right? Yeah. I think this is the velocity that they're talking about because what other thing could they be talking about, right? Uh, okay. So you can figure out what delta P is. Yes, you can do that. You can also figure out what L is. I mean, we know that, of course. You can't figure out K, unfortunately. Or maybe can you? Uh, so this whole thing is kind of a constant, isn't it? So V naught changes throughout. So by continuity, of course, V naught is the same throughout, right? Yeah. And then here's the gradient, sure. And then, so there's no escaping that we need R squared. Otherwise, we won't be able to do anything. So then without R squared, how do we do it? And why did they give us the density? Oh, they give us because we want the pressure at this point, right? So that will only be possible by the hydrostatic pressure formula. And okay, look, I don't know what this area is of the cross section. So how am I supposed to do this thing? There's R squared involved in there. You will need something to do it, right? Yeah, okay. I need that R squared, but they didn't give me what the R square is. So now what? They did give us the pressure at that point. Okay. You can't just apply Bernoulli's over here or here. Can you? Okay. What about along this streamline? No, you can't. Okay. So you have that V naught throughout, and right, that just won't make sense. Uh, you can't apply Bernoulli's. That's a problematic thing, isn't it? What about the continuity equation? Okay, it might still work because the velocity profiles are different after you enter into it. Before entering, it was slightly different, right? Even then, you could still have the same Q, but then the central velocity is different now. So you can't apply Bernoulli's equation anymore. This is awful. Oh God. Uh, think something, just something, you know. Oh, I know. I think I know. So you can apply Bernoulli's equation, but only at this point and that point. Although you can't apply along the streamlines after that anymore, you can still apply it along this and that. And then what you will do is that you will just assume that since it's just starting, the velocity profile was so it's the same velocity throughout the cross section. You can assume that, and what that would mean is that you will be able to figure out the q value with just velocity times area, and there you go, right? So once you know what q value is, yeah, okay, it will just become a piece of cake, isn't that right? Sure, it will be nice actually. Awesome, yeah, right. You can just get the q value in that way. Although we won't be able to know what E naught is directly through that. Uh, Fine. So then this equation KLQ, you can actually figure out what Q is. So then you know this quantity, you know this quantity and this quantity. So you can actually figure out what K is, right? Yeah. Once you know what K is, um, right, and then what will K actually be? K will just be, where did that go actually? Oh, okay, we know that, right? We know what the thing is. So delta V upon Q is equal to 8 eta L upon pi r power 4, right? So this is not there. This is not variable. So now you know what this K thing is, and through that you actually know what this R square terms. Awesome. That does it, right? Isn't that just awesome? Yeah. So once you know what R is, all you need to do to figure out the velocity is, you know, use this equation, and then you have the thing. Yeah, right, right. Or you could just use this directly. Oh, okay, so that's not supposed to be happening. Yeah, you can just use this directly, right? So use this equation. So you just have delta p equal to 4 eta L v naught upon r squared. That you can use. And also you can figure out the v initial using Torricelli's theorem. Basically just v initial equal to square root of 2gh3. So this times the area of this thing, right? So this times pi r squared, that's equal to our q. So our q is just pi r squared times square root of 2gh3. But that's also equal, wait a second. Oh, oh, okay. I see there was no need for doing all of this. There was no need for doing the delta p thing because we already have the easiest way to figure this out. Okay, fine. Just use Torricelli's theorem to get this thing. So at the very start, you can figure out the velocity, but the thing is the q will be the same at the start as well as when you have kind of steady flow, your q is still the same. So then this is equal to this thing, pi v naught r squared. Yeah, okay, that's the way you can do it. Huh. I was thinking of something completely different. I was thinking, okay, the heights are in linear fashion so that you can just figure out the slope is and everything like that. But you don't need to do all that. Just use continuity and then you get the thing. Yeah, awesome. So what that means is, oh, and sure, that was the thing. Sure. Uh, or should be r squared. This cancels. So we just have v naught equal to 2 square root of 2gh. And in fact, this looks, you know what? We can always do this thing. So v naught or v max or whatever, that will just be equal to 2 times the flow velocity that was initially in there, right? Yeah, you can do it all the time. Awesome. And now in this case, you know what the flow velocity is. So just this thing. So you actually know what the flow speed is in the center, right? Yeah, right. Awesome. Find the velocity of the liquid flow. It's going to be this thing. Okay. So v naught is equal to 2v initial, which is equal to 2 square root of 2gh3, right? That's our equation. And this will be what? 2 square root of 2 times, what is g? The weird thing is that actually they gave us h2 and h3 and whatnot. So yeah, I mean, that was weird. Why did they give us those things? And what is, so all this is L are equal. They actually didn't give us what L is. Yeah, they gave us the density and they gave us h3. I think that's all we need to figure out what V naught should be, whatever. So G is 10 and then h3 is 35 centimeters. So 0.35 meters. This will be what? 2 square root of is like 0 0.7 times 10, just sort of something. This is 2 sort of 7 meters per second. Cool. I've never seen a question like this because, yeah, it involves this. It's very weird. It's just really weird. I've never seen this before. So before having the velocity profile that you have in Poisson's equation, you have the usual velocity profile that everything has the same u vector, right? And then it turns into that, and the only thing you can actually use is the continuity equation, right? Because everything else is just, yeah, we don't know what's happening as it becomes the different profile, right? So only thing you can use is the continuity equation, and that's how we got E naught. Anyway, next question. 336. The cross-sectional radius of the pipeline decreases gradually as r equal to something. Okay. Wait, what? The pipeline cross-sectional. Oh, okay. I think I know what you're talking about. So it's like this, right? So this is the pipeline that we're talking about. Fine. Where alpha is something. Okay. X is the distance from pipelet inlet. Okay. Find the ratio of Reynolds number for two cross sections separated by delta x is equal to this. I have no idea how to do this one. I mean, you can use the formula that they give us for Reynolds number, but then that was for a cylindrical cube. It was not for something like this, or a cross section of this. Yeah, it was not for that. How am I supposed to? Oh, it decreases gradually. I think that's the important part. It decreases gradually. Okay, then maybe it's just doable. So once again, what is the Reynolds number? Uh, oh god, I always forget the thing. So it's I can't remember it. Can't remember it. Reynolds number. So the Reynolds number is rho u l. What is L? Characteristic length. Okay, in this case, it's just diameter, right? So rho u diameter upon eta, which I would like to say is 2 rho u times the radius upon eta. I think that's better. Yeah. So that's the Reynolds number. Okay, awesome. What do you want? 336. Where is that? Wait, okay. When we said u, what do you mean by the velocity value? Okay, which velocity value? Because we're talking about viscous fluids, so oh, huh. I think the middle velocity, right? What else could it even be? Okay, 336. Okay. Find the ratio of Reynolds number for two cross sections splitted by something. Okay. So the u thing though, what do you know? You know that u times of r squared is kind of constant, right? Yeah. Um. Okay. So Reynolds number 1 upon Reynolds number 2, that will, this is constant, right? So it's just u1 r1 upon u2 r2, which is like the u is proportional to 1 upon r squared is just r2 upon r1. right? It's proportional to that thing. Okay. Or you can just say Reynolds number 2. Okay, the inverse is also true. So RE2 upon RE1 is equal to R1 upon R2. Awesome. And now we know what R is. So just this thing. So RE2 upon RE1 is equal to R1, which is this thing. Okay, that R not cancels. We don't have to look for that. And then just 1 upon 1 there. Okay, cool. This e power alpha x2 minus x1. Yeah, that looks cool. So that's the ratio. It's just e power alpha delta x. Yeah. Which is what? E power, what's alpha? Alpha is 0.5, just 1 upon 2. Just figure out, yeah, just calculate this right now. It's e power 1 upon 2 times delta x is 3.2 meters. So this is e power 1.6. Have I seen this before? 1.6. Natural log of what is 1.6? I don't know. There's something with an e for sure. There's something natural log of. I don't know. I don't know what is natural log of. Okay, e power 1 upon or 1.6, right? Hmm. Think. 0.6. This is a problematic thing. It's like e power 3 minus 1.4. No, it's not helping. I think 1.4 is like 2 times of 0.7. I can try to do this. So just e power 3 upon e power 1.7. Sorry, 1.4, which would be e power 2 times of 0.7. So e power 3 is approximately 20, and this thing is e power 2 times of natural log of 2 approximately. So this is 2 power 2, which is 4. So basically 1.6 is natural log of 5. Okay, so this thing is approximately 5. Yeah, natural log of 5 is 1.6. Okay, interesting. Oh, I remember I made a mistake somewhere recently where I actually put natural log of 5 as 1.71. That's definitely wrong. Natural log of 5 is 1.6. Yes. Okay, awesome. Next, 337. What? Sorry, when a sphere of radius something moves in a glycerine, laminar flow is observed if velocity of sphere does not exceed something. Okay. At what velocity of a sphere of radius something? Okay, will the flow in water become turbulent? Now this question is something I don't know. I don't know what to do. You have a sphere moving in liquid and that causes turbulence. What? How do you measure that? Huh? Uh, I have no idea. Like, how do I proceed now? What exactly is the Reynolds number going to tell us though? Maybe it's like you can apply Reynolds number at different points. And no, but it involves a characteristic length, and that's not. Yeah, okay, you can't do that. I don't know. I don't know how to do this one. Yeah, just move on. This is weird. 338. A lead sphere is steadily sinking in glycerine whose viscosity is equal to this thing. What is the maximum diameter of the sphere at which the flow around that sphere still remains laminar? Once again, the same as the last one. It is known that the transition to turbulent flow corresponds to Reynolds number, this thing. Let us click on that sphere's diameter. I don't know why this is supposed to be the thing. Okay. And the next one is also similar, right? Okay, the 339 is actually doable because it only involves viscosity and nothing about turbulence, right? So 339 is doable, but 338, Okay, the characteristic length is taken to be the sphere diameter. What? What is this? Okay. Uh, so what is our u that we put? I think the speed of the sphere. I think. Okay. Wow, this is just so bad. So what was the thing? Rho v L upon eta. That was a formula, right? Yes. Um, let's be honest, and in this case it's like rho to okay 2 rho L say 2 rho v r upon eta, right? Okay. So let's be study this thing, sinking in glycerine whose viscosity is equal to this thing. What is the maximum diameter of the sphere at which the flow around that sphere still remains laminar? It is known that the transition, wait, maximum, oh, okay, fine. Uh, right, let's try to do this thing. So this is the Reynolds number, and this should be, less than 0.5. That's our condition. So that is remains laminar, right? I think so. We can figure out what V is. That is actually doable. So 6 pi r eta times the velocity. Right, so it's steady thinking, that just means it's at terminal velocity, and this is equal to so this thing is equal to the effective gravity stuff. So yeah, 4/3 pi r cubed times the density. I should put a g over there as well. So that, yeah, so this, and then you just have the density of lead minus density of water, right? Okay, and in this case you actually want density of water, I think, right, in this formula. Okay, I'm just gonna put it like this. So it's rho naught minus rho, where rho naught is density of lead. Okay, so rho naught is density of lead, rho is water. Awesome. So then you can write b as a function of r. Some stuff cancels. This becomes r squared, and then this becomes 3. This becomes 2. It's like this is equal to 2 upon 9. Then you will have r squared g upon eta, right? And that's of rho minus rho naught, or rho naught minus rho, or whatever. So we just have to put that in there. So Reynolds number will, actually just put, yeah, we'll be using this formula in any case. So yeah, just leave it like that. Then Reynolds number will be what? 2 rho VR upon eta. So 2 rho R upon eta times V, which is this thing. So let just 2 upon 9 R squared G upon eta rho minus rho. Yeah. So just have eta squared inside. Okay. The square 9 over there. You got 4 rho G. Then you got rho naught minus rho. Then you have R power 3. Yeah, that's your Reynolds number. Okay, and what do you want? You want when will this become 0.5, right? Yeah. Uh, okay, this is just really bad. Anyway, still some stuff. So you got V, which is our terminal velocity, and you also have the Reynolds number. Awesome. So now what? Now you just want this to be 0.5 and solve, right? Yeah. So just have R cube is equal to 9 eta squared upon 8 rho minus, so okay, rho naught minus rho, the rest of G. Yeah, right. So basically R equal to cube root of all that. Yeah, that was cool. So R is just equal to, and wait, what are we looking for? What's maximum diameter, right? So we just want 2R. So just actually send that 2 over here. So the diameter, so D max should be equal to this thing, the cube root of 9 eta square upon rho times rho naught minus rho, times G. We don't know what density of lead is, so just leave it like that. Okay, that works out. Yeah, this is our final answer. Okay, 339 is doable, I think. So a steel ball of something starts sinking with zero initial velocity in olive oil, whose viscosity is this thing. How soon after beginning of motion will the velocity of ball differ from the steady state velocity by eta equal to 1 per, so sorry, by n equal to 1%. So okay, it changes by 1%. That's what you're saying, right? Yeah, no big deal. It's doable. So let's write down some equations. The force on this thing, right? So this is the mass times all that we want to do. M negative dV upon dt, of course. This gravity that's pulling it inside. Oh, okay. This is supposed to be positive in that case. So this gravity pulling it inside. You just have the, what am I saying? The volume of this thing, that's the density of steel minus density of water. You know what? Just use rho naught for density of steel, just like we did last time. So naught minus rho times g. That's gravity, and uh, right, plus, sorry, minus, because it will actually pull it up, right? Yeah. So minus 6 pi r eta times the velocity. Yes. Looks cool. Which means the density is dv upon dt is equal. Okay, it should be the density of this thing, of course, like density of steel. And that's equal to what? Rho naught minus rho times g, and minus 6 pi r eta. It's not the volume, it's the velocity. Sorry, 6 pi r eta velocity upon the volume, the actual volume, which is 4/3 pi r cubed. So you just have 9 upon 2 over there. And then just have r squared. Like it's just 9 upon 2. Okay, first of all, what is this thing? 9 eta velocity upon 2 r squared. Okay. So that's our differential equation. Solve it. I kind of hate this actually. Yeah. So just divide by rho naught, of course. Just have dv upon dt is equal to, this looks awfully like I've seen this somewhere, maybe. Yeah. This looks bad actually. Very bad. Uh, will happen again. So just yeah, first of all, what I'll do is actually I'll pull out some constants from here to make this just v inside. So this will be 9, so negative 9 eta upon 2r squared, and that's pulled out. This will just be what? V minus, yeah, rho naught minus rho, that times of 2r squared. Okay, this thing. 2 rho naught minus rho r squared g upon 9 eta, right? Maybe we should just call this a constant now, whatever. So dv upon dt is equal to what? Negative 9 eta upon 2r squared rho naught, of course, times v minus all that stuff. So v minus 2 rho naught minus rho r squared g upon 9 eta. Yeah. Okay, awesome. So you have the equation now. And what do you want? Okay, first of all, figure out the solution, right? Okay. So what we'll do is we'll just say this thing is A. So we'll define A to be, or let's say K, yeah, K is better for this thing. So K is equal to, okay, K is equal to 9 eta upon 2r squared rho naught. And we'll just say, V naught is equal to, so V naught will be the velocity finally, right? So after infinite time, V naught will be, because that's when dV upon dt will become 0. So V naught will just be this thing, 2 rho minus rho naught r squared g. Okay, what was the V naught that we got previously? Yeah, the same stuff. So upon 9 eta. Okay, so then this just becomes this thing. dV upon dt is equal to negative k times V minus V naught. Then the differential equation just has this answer: V minus V naught is equal to e power, I should say this, is equal to, so initially, wait, no, actually I should say finally, right? Well, whatever, just do it a proper way actually. So natural log of V minus V naught, as it goes from V is equal to, initially it's just 0, right? And finally, let's say it's just something V, right? Uh, oh God. Oh no. Oh, this is a problematic thing because, okay, so it's actually increasing, huh? Whatever. Does that even matter in the end? It doesn't, right? So this is just equal to what? Negative k dt. Indication of that is just kt, which means natural log of v minus v naught, or v naught minus v, I think that's better. So v naught minus v upon v naught is equal to this thing. So what does that mean? V naught minus v is equal to v naught times e power negative kt. So v is just equal to v naught times 1 minus e power negative kt, right? Where you have v naught and v as we defined. Okay, sorry, v naught and k as we defined. So what was our answer? What was the question? Sorry, it was how soon after the beginning of motion will the velocity of ball differ from the steady state velocity by eta equal to 1%. Sorry, by n equal to 1%, right? So what does that actually mean though? It means that v is equal to, it will of course be less, right? So v naught times 1 minus n, I think. I guess that's the thing. That basically happens when n is equal to e power negative kt, and n is of course just 1%, so 100 is equal to e power kt. That will happen when t is equal to 2 natural log of 10 upon k. All right. So our answer is just that. So the answer, t is equal to 2 natural log 10 upon k, which is what? Let's actually figure this out. And first of all, just put k over this. It will be this thing: 4 natural log of 10 times r squared. So just put it this way: 4r squared rho naught natural log of 10, and all of that. Is that correct or not? Yeah, it is. So upon 9 eta, just that. Looks cool. Yes, this is our final answer. Just put that like that. Okay, we don't care about that because we can just create things like that anyway. So yeah, this is the answer, which is what? Let's see. I think we should have used n as the thing actually. So then instead of writing this, you just write God, the negative and all that stuff, right? Yeah. So this was what, 2 natural log of 100 basically over there. Yeah. Which is like natural log of 1 upon n. So just negative 2 all of that and then natural log of n. Yeah, that looks cool. This will be the answer. Let's actually calculate this thing. So it is negative 2. What is r? Oh, okay. You need the density of steel in any case. So let's not do that. Okay, next. It's done, right? Oh yeah. Then next you have what? No, 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 no. I'm not gonna do all of this. Relativistic mechanics. Look, I won't benefit from it. That's why I won't do it. I might do it after a month or so because I have an upcoming exam, and that's why I'm doing this whole book because I might benefit from it. But something like this, I won't. I'll do it later and much later. Okay, this does look interesting though. I have a bit of experience with Lorentz transformations, not with this stuff, but yeah, who knows? Maybe I'll do it in proper detail at that time. Anyway, so we won't be doing this. And what will we be doing? I think no, we should just stop. We should stop here. Yeah. So for a month, I won't be doing Irodov anymore, right? Because Newtonian mechanics, it's done. The next major thing will of course be electrodynamics, which yeah, is like a completely new thing, and I don't want to spend time doing that in detail because it's just a very big subject. So yeah, we'll stop over here. That's it. I'll see you guys in the next video.